So here we are, and in this really precious morning, I think we now move on to our last speaker, which I welcome, Roberto Casati, and the title of his lecture is "Shadows in Painting." And Roberto Casati is a philosopher and member of Accademia Europea, research director at CNRS, and director of Institut Jean Nicot in Paris, and professor at EHESS. Casati worked on issues related to the perception and representation of space and objects in space. He has published more than 150 articles in scientific journals or collections, several books, and has taught and done research at SUNY Buffalo, Turin, Istituto Universitario di Architettura in Venice, Dartmouth College, and Columbia University. With Achille Varzi, he published two classic contributions at MIT Press, Whole and Parts and Places, and also at MIT Press, along with neurophysiologist Patrick Kavanagh, he published The Visual World of Shadows. He presents research concerns. His present research concerns navigational tools as maps or GPS to remedy disorientation, and this would be the object of his forthcoming book, The Cognitive Life of Maps, that will be published by MIT Press, and conceptual negotiation regarding environmental problems, particularly in the marine environment. And part of his research takes place in ocean crossings on sailboats, as Transat, which is I think Pacific, no? Atlantic, sailing through the Atlantic in as far as I know, quite small sailing boats, and is documented in Oceano and in the anthology The Sailing Mind, which has recently appeared, published by Springer. So it's really we are really thrilled to have you with us, Roberto, this morning. We also thank you very much of your presence, and also because I think you are part of our advisory board, because you are a member of this Youth for Difference advisory board, so your presence is also precious for our project as a whole. So thank you very much. I leave you the floor.
So thank you very much again. So I will be very quick by way of an introduction. So it's correct that I moved my research from studying some of the computations the brain uses for dealing with shadows and perception in general from a philosophical point of view, but also with a neuroscientist. And it's true that I moved from that to research on the marine environment. They're both kinds of spaces we represent somehow. And I just would like to show very quickly a go-between between the two researchers, because it looks as if working on shadows in painting and working on the marine environment are really disconnected areas. But I would like to give you a very quick overview. This small slide shows an area between the sea bottom and the sea surface, which is called the mesopelagic area. It is remarkable because you don't have any way to hide into the mesopelagic area. It's not like the bottom sea of a sea, which you have hiding, or the sea surface. So flying fishes can fly over and hide somehow in the air. In the mesopelagic area, there are no hides. And so what happened there is also difficult to have speciation because you don't have islands. It's just an uniform thing. The only non-uniformity is the light gradient, and evolution has found a way to take advantage of a light gradient by generating counter lighting in some animals, which have a light bottom and a dark top. So but when you look from them, at them from the top, you don't see them against the dark bottom. And when you look at them from the bottom, you do not see them because of the counter lighting they produce by different ways of bioluminescence. And this is one of the areas I'm working on right now, is understanding the role of plankton in this. But there is a point which brings me to what I'm going to say today, is that light and shadows have been the only ways for inhabitants of the mesopelagic area to develop different types of species. It's the way in which these species take into account the light in the environment and the light of other species that created this incredible variety of life forms in the mesopelagic area. So it's just a minor point just to stress a potential connection. Actually, the cover of my book with Patrick Kavanagh was somehow talking about this move that I had in mind from shadow study to the sea. So the book and the topic of paintings. If, in a sense, what I'm going to say today is exactly in the opposite direction, and there is a lot of overlap with what Vittorio Gallese just said, but he has an approach which goes from neuroscience to art. That is, try to use neuroscience to understand art, understand how we relate to artworks. And he did an impressive work on some of the aspects of this understanding, together with David Friedberg, whose publications I recommend highly, especially The Power of Images, common friend. So I'm doing more or less the opposite, that is trying to use art for understanding the visual brain. So I'm not a neuropsychologist. I direct a lab which is full of people working in cognitive science, and we are part of a lab in which there is a lot of neuroscience, so I talk to neuropsychologists a lot. But I teamed 15 years ago with Patrick Kavanagh, who's one of the top visual scientists, and who had a strong interest in shadows, to look into the artistic contribution to neuroscience. This is our point. So artists are neuroscientists in a sense, because they uncover some of the hidden computations of the visual brain, and then we have to look into the brain to see whether these things are confirmed or not. So I could spend hours on the next slide, but I'm not going to do it, but I just give you a very quick overview of what goes on here. It's a kind of a roadmap. Shadows are part of our visual environment. They are very, 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 very salient in the visual environment. If you have shadows in the environment, there is a lot of noise created by them. So the visual system spends a lot of time trying to tell shadows from non-shadows, a shadow from a dark spot, a shadow from a black area. And once it does it, it tends to filter out shadows, basically, because you don't want to see them, and you don't typically see them. You have to pay attention to see them. And then it uses shadows in two ways: by going to the conceptual system or by going to some kind of proprietary algorithms, which use them to reconstruct the visual scene. So there is a lot of, the visual scene is a result of some kind of reconstruction. It's not given automatically. Your brain does a lot in order to interpret what is in the primary scene, and this work partly goes through shadows. So let me go through it. This is an example of shadow noise. So when you have very strong shadows in the environment, shadows have the highest contrast in a scene. Typically, the contrast between a shadow and a non-shadow on a white surface could be much higher than the contrast between a black surface and a white surface. And so they introduce noise. It's very difficult to read this scene. It takes a while. I mean, you see there are some hanging things and the shadows are clearly positively creating noise in your scene. They can create so much noise that they are taken for things. So you have a small shadow here, on the right, which looks as if it is the shadow of this other shadow. So this shadow here becomes somehow concrete, and it generates a shadow of itself. Okay, I was saying that shadows sort of become objects sometimes. They compete with objects. So in this picture here, you do not know where the object ends and where shadow begins. Let me try the full screen, you're right. And so I'm not going to have a totally structured presentation. I want to go through a number of images, and I'm going to make comments on those images. So this is an artwork by an artist that I like a lot, Larry Kagan. It's called Implausible Container. What is this artwork about? Well, you have a jumble of wire at the top, which is fixed to the wall in a point. I think it's over here. And then you have a light which is not visible. And when you switch on the light, the shadow of this messy wire is the box down here, which is sort of surprising because you don't see any way in which this thing down here could be the shadow of that thing over there. Of course, he spends a lot of time trying to use the light on, and then he bends the wire so that the shadow becomes this type of thing that you see down there. And here is a case in which the visual system has no cues. It's not able to make a connection between the object and its shadow, because it's very implausible that this thing is the shadow of that object. Here is another example of, say, conscious, reflective attempt at understanding how a shadow works. So this is a beautiful picture of one of the shuttle launches. And there is, as you can see, okay, the puff of smoke, the plume going up here, and then it goes towards entering the orbit over there. So there's a perspectival effect. It's not falling down, it's just going up and up, but there is a perspective here. And there is a moon here, and this strange blue ray coming from the moon, or you never know what it is. I mean, it's very difficult to understand what this is. And basically, this is the shadow, this blue thing here, the atmospheric shadow of this part of the plume. And as it is full moon, the sun is opposite to the moon, and the shadow almost focuses on the moon. So again, difficult to understand what is this shadow of. We can, by having some notion of astronomy, notion of technology, and a number of things, understand that this blue thing here is the shadow of this part here of the cloud. But these are not cases of quick and fast use of a shadow by the visual system. And another classical example of slow uses of shadows are the way in which Galileo or many astronomers, until technological observations of the sky in the 20th century, use shadows to reconstruct shapes on the moon, or by eclipses, or by phases, to understand the different positions of bodies in the solar system. There is a long story to be told here, and of course I told part of it in a previous book on shadows, but it's fascinating to see how many discoveries, astronomical discoveries, have been made through careful observation of shadows. One is very beautiful. One is the understanding that the Earth has a size which is much larger than the size of the moon. This was made by Aristotle, who didn't have this type of beautiful time-lapse images. But if you check the profile of the shadow of the Earth, as the moon enters, like in this direction, the Earth's shadow during an eclipse, well, you can see that the Earth has a size which is much larger than the size of the moon. And that was an interesting discovery already 2,500 years ago. So this is what we could call system 2, so slow, conscious, using working memory, using attention, processing of shadow in light. But then there is also what we call system 1, processing, which is fast and conscious. And there are many art examples and uses of idiosyncratic algorithms. Classical case, everybody talks about an illusion here. It's not an illusion, but it's a classical case is the following. So an example by Adelson. I think everybody should know about that, but I want to make a couple comments on what this is like exactly. So you can see here there is a shape on a checkerboard, a green cylinder on a checkerboard, and it casts a shadow. So the shadow covers some areas here in the middle of the checkerboard, and these areas clearly have different colors. So there are, on the checkerboard, there are light colors and there are dark colors. Now, the interesting point is that when you measure the luminance is the light coming to your eyes from the case A and the cell B, where the luminance is exactly the same. It corresponds to the luminance of that patch over here. And I can do this in the next slide. So if I move the patch down there, you can see that A and B have exactly the same luminance. But of course, this is not what you see here. It's not what you have the impression of seeing. So what happens here? It happens that the visual system is not interested in the shadow. It just killing the shadow out and tells you, well, B here has a luminance, which is the result of subtracting B's light, subtracting the shadow's contribution to B's light, B's actual reflectance, that is the light that it would reflect had the cylinder not been there. And so the visual system is already calculating at a very peripheral level and eliminating shadows so that it can give you the true structure of a checkerboard. The true structure of a checkerboard is a two-color checkerboard and not a checkerboard with many different colors. And A and B have clearly different colors on the checkerboard. So this is not an illusion, basically. This is a complex mechanism which is uncovered by the use of a shadow on a checkerboard. You can have other ways to kill the impression that A and B have different color. But of course, these are ways in which you are already manipulating the image for your brain to do this. So the shadow computation we are talking about are used by the brain to reconstruct 3D, and they reveal some aspects of internal code which is used by the brain. Although we don't know anything about the specifics of the code, we know that it has to conform to certain constraints. Interesting point, in light, there is much more information than used by vision. So there are many things in light which vision could use and it cannot use, it does not use. And also, and this is what we call the incompleteness of vision. Vision is not taking into account everything which is out there. It only selects things which are interesting for it. Vision often, and this is the opposite, does not conform to norms of geometry and physics. So there is some kind of inconsistency, which means that psychology is interesting or neurophysiology is interesting. We have double dissociations. There is tolerance for impossible shadows and intolerance for permissible shadows. We see some of these examples because painters revealed these facts. But it is important to know, if vision was just a way to register what is out there, there would be no incompleteness. It would register everything, and there would be no inconsistency. It would not represent things which are not there. But vision is doing something more. It's contributing to the construction of a visual scene. So this is one example. There are things that we do not like at all. So vision does not consider the picture on the right, on the left, as a picture of a body with a shadow, because shadows cannot be lighter than the surrounding background. That could be maybe a patch of light which is cast by a hidden lamp, but not a shadow. On the other hand, shadows, this on the right could be considered as a shadow by visual system, although the color is completely impossible from the physical point of view. So there is no tolerance for beyond certain parameters, but some parameters are really irrelevant for having what we call the shadow character, being recognized as a shadow. Once you have shadows, you have 3D. And this is a fantastic example of the way in which the visual system takes into account the presence of shadows, that is difference in darkness and in lightness, and the fact that in the environment, light comes from above most of the time. So when you look at this, most of us, if not everybody, most of us see a normal footprint on the left, a normal footprint, something that you and I could have left on the sun, and an impossible footprint on the right, some kind of the footprint of someone with a concave foot, which is impossible or horrible. Okay, now the shadow on the right corresponds to a type of physical reality which is clearly not possible, and you know about it because you know about biology, you know about your field. Still, you see it. You see what you see on the right as some kind of convex structure. What happens here? The visual system interprets shadows and light as coming from a source of light which is ahead of you, on atop of you. So lights come from above, and then the pattern of darkness and lightness in this picture is only compatible with a certain structure of the two footprints, convex here and concave here and convex on the right, so that the visual system can only see that as the way you have, even though it is an impossible footprint on the right. And in doing that, we claim, people have been claiming this at least since von Helmholtz, that the visual system is performing an inference. It uses as a premise the pattern of light and shape on the photograph, and knowledge of the fact that unconscious knowledge of the fact, or statistical unconscious knowledge of the fact that light comes from above. Important point, these two pictures are exactly the same picture. That is, the picture on the right is the picture on the left, which has been flipped over 180 degrees. But they are the same pictures, and they're interpreted in totally different ways because of this assumption that light comes from above. And Patrick Manassian did a fantastic experiment on that. So you have this structure which looks as if it is, you know, those kind of chocolate boxes in which you put the chocolates at the bottom of it. And here clearly you have some small indents, some small holes in it, or the opposite, or seen from a different point of view, say, a chocolate box in which you have small bumps. And actually, again, this is the same picture, just turned 180 degrees. In one case, your knowledge of the fact that the sun comes from above makes you see holes, and here makes you see bumps. But it is exactly the same picture. When I do this physically, I take the slide projector and I turn it around so that people can see that this is exactly the same picture. Same picture, two different interpretations because of different types of knowledge which are used into that. Shadows are used for getting distance of objects from surfaces. So the same square over the same background is seen as closer to the left and more distant to the right, just because of the displacement of the cast shadow and the size of the cast shadow over here. This is used also, you can use it in determining the depth of sea, which is the shadow, which tells you that the boat is not flying. It is on the surface, but it looks as if it is flying because the shadow is telling you the distance between the boat and the surface. So let me go through some artworks here. Visual system has to recognize when a shadow is a shadow in order to use it as a shadow. So I don't know if everybody, maybe many of you know already, but if everybody can see the Dali ambiguity here. In the middle of the picture, you can see either of two things, but not two things at the same time. On the one hand, you can imagine this is a pedestal, and there is on top of it a bust of Voltaire. You can see the eyes of Voltaire, the nose, the chin, and the shadow under the chin and under the cheeks. Or you can see two nuns. These are the eyes of the nuns, and these are the heads of the nuns. So you have to, if you can see either of them, you cannot see both of them at the same time. And the way you see them suggests a different contribution of these black spots to the reconstruction of visual scene. If you see the statue of Voltaire, all these things here are seen as shadows. So the statue is just white, it's not black and white, it's only white. If you see the nuns, the black things here are the color of the gowns, and they are seen as dark spots and not as shadows. So the reconstruction that you do influences your follow perception. Shadow character is the way a shadow is seen against an environment, and you can modulate it, you can kill it. You can do a lot of things to a shadow so that you do not see it as a shadow anymore. The visual system here is interpreting this as an absurd coincidence. It's very unlikely that a shadow is cast exactly on a kind of a zebra or leopard surface. So it tells you, okay, this is not a shadow, this is a kind of a drawing. Same thing for lines. If you do not draw lines around the shadow, you can see, this is Giorgio Kienner's, with an outline removed, you can see a face here, smile, eyes, hair. There was experimenting with this type of so-called Mooney figures. And but if you add the lines, you do not see, you just see a kind of a geographic map, and you cannot see the face anymore in most conditions. So we immediately see that some things are impossible, like the Penrose triangle. So you can see that no physical structure can correspond to that, but it's much more difficult to tell which of these three shadows is impossible.
12:30.
So which of these three shadows is impossible? If you ask people, they have difficulties in finding out the impossible shadow. And it's much more difficult, at least, than finding out that this is an impossible figure. So the impossible shadow here is the one on the right, which means that we do not have an immediate shadow conformity calculator as we have an immediate object conformity calculator. So in calculating the shape of this object, we go around and, okay, at some point we see it's not impossible to go to recede in the image. But here there is no way for visual system to do this type of calculation unless you do it explicitly in so-called system 2 mode. So you might not spot anything about this shadow, it just goes unspotted. And actually this shadow is the shadow of a woman glued to the shadow of a man. But still, it still works as a shadow. It still tells you where the man is relative to the sidewalk. And this has been known by painters for a long, long time. So they discovered many years ago, many centuries ago, that you can cast, you can draw very absurd shadows and they still work. So this is the shadow of Dante. Is important in the story because the souls in the purgatory discover that Dante is not one of them because he can't cast a shadow. And still the shadow is completely absurd. No person could cast a shadow like that. And probably the thing that could cast a similar shadow is kind of a figure like that. So moral of the story, you can draw shadows which are impossible, but they still work as shadows. And this is a big neurophysiological discovery. It's a big neurophysiological discovery in the sense that the visual system can use a lot of image compression in order to retrieve 3D. It doesn't care about some of the details. Even though you can be looking at the details, the visual system is not caring about them, and it still gives you a sense that Dante is not flying in the air, but is solidly on ground, and it has some kind of bodily presence. So Masaccio in the Campella Brancacci, another discovery. So you can cast shadows on the ground which are not present on the bodies. It's a kind of carpet shadows that pass under the bodies, and they still work. I mean, it looks as if there is a big thing here which is casting some shadows here, and shadows in water as well. But these shadows are impossible. I mean, you cannot have shadows that go under bodies without climbing bodies. And somebody did a simulation about that, so kind of replica of a Brancacci, Miko Kuwabara in Japan, one of my students there. And so you would see all these shadows on the bodies, which are not present here, but unless I told you, nobody would have cared, which means the visual system is not caring about that. Not in the sense in which it is caring about the impossibility of the Penrose triangle. You can have shadows that pass under bodies, and nobody cares, basically. You can have shadows, this is in Perugia. Oh, sorry, the other one was a Korovitz. This is Piero Francesco. So the shadow stops at the wall and does not climb the wall. Shadows, again, can turn around corner, which is impossible. So there is no optics which supports the shadow turning around corners. And these are cases in which impossible shadows are tolerated. So let me say something about the methodology. How did I work for doing this? Everything that you see here is the result of physical observation. So it's not pictures from books or from websites. I have a database of about 3,000 sketches of shadows in different museums when I went in many museums in the world, because the images on a PC or on a book are not very well equalized for the shadow contrast. So I went around and spotted all these different cases of shadows, and this is the methodology that I use. So maybe today we should do something different, trying to train some algorithms. Maybe I'll do that at some point in order to discover strange shadows around in paintings. But already this small phenomenology is telling about the operations which are performed by the visual system. So these are other cases of shadows. So truncated shadows, they do not climb a wall. Ghostly shadows. The interesting point that these shadows are strange only for people like me who spend a lot of time observing them. But if you talk to people in museums, they do not care at all about the shadows, which means that the visual system does not care. Shadows that climb stairs in an impossible way. This is one of my favorites, is Filippo Lippi in Spoleto, a nativity. So you can see that there is a structure. So the typical structure here is that there are ruins, and in the ruins of the former order, the Roman order, the imperial order, there is the Christ and the nativity, and the ruins are such that you have poles protruding from them. Some poles are parallel to the painting surface, and some poles are perpendicular to the painting surface. And you have a lot of light coming down, a lot of shadows. All the shadows seem to be perfectly consistent. That is, they all go from the top left direction over here down to the bottom right direction. But for a shadow to come towards you in this part of the scene, the source of light should be beyond the wall. And for a shadow to be cast onto the wall, the source of light should be on your side of the wall. So shadows here on the right and shadows here on the left are absolutely inconsistent, impossible to have in the same scene. And again, it looks as if the visual system is computing shadows on the 2D surface, only on the surface of the canvas, and say, okay, these are all parallel, so who cares? Everything is fine. This is an example. So this is the correct projection would be like this, and this is the Filippo Lippi projection. It looks as if this is right, it looks as if this is wrong, but actually this is the right one and this is the wrong one. And if you look at the same scene from atop, shadows point in completely different directions, and it looks as if this is an incorrect projection, but this is generated by the computer, so we cannot do better than that. So Fra Diamante Di Feo, who's a student of Lippi, decided to correct the master in this painting, which is now at Louvre. Fra Diamante was active in Prato. And you can see the correct solution to the Lippi problem. So the shadows point in different directions because the source of light is on this side of the canvas. And there is also a small bird here, probably who's singing victory for Fra Diamante. Inconsistent shadows are everywhere. Here's a more recent example from the Chirico Piazza. So this is not a shadow, this is a reflection. There is no way the statue can cast a shadow like that. The hand should be on the other side, either of the statue or of the shadow. But still, maybe we are using here some reflection module in order to decide if the shadow is acceptable. Of course, there are cases in which a shadow is acceptable in a reflection way, but the source of light should be in a completely different position. Hiroshige, there are very few shadows in Japanese ukiyo-e and graphics in general. So he was experimenting a little bit with night views, and you can see there are things here which are halfway between shadows and reflections, because it looks as if the surface here is a wet surface, because the reflections are continuation of the shapes, and they're not related to the light, which would have reflections points towards, shadows points towards the moon, and not points toward the projection of the moon on the surface here. Again, what we should claim here is that painters were experimenting with verisimilitude. They were trying to give an impression which was sufficiently accurate to be recognized as plausible or correct. They were not caring about precise scientific accuracy, and they were taking advantage and thereby discovering some shortcuts of the visual system when it was dealing with shadows. And the same here. So these are silhouettes projected on a screen, but this would not be possible as silhouettes. So maybe there are transparencies, it's not clear what they are, but if there were silhouettes, they would be impossible, and still they're seen as silhouette by our visual system. A couple of final examples. One is what I call the copycat effect. So a very simple way painters have to make shadows is to copy the outline of a figure which casts a shadow, which is what we did in the figure on the left. So in the figure on the left, I just took the shape of the red cube, made a silhouette, copied it to the right. Took the shape of the yellow bar, made a silhouette, and copied to the right, and so on and so forth. And it looks like these are shadows of the four objects. If they are, you would see that the four objects are in a kind of a plane which is parallel to the surface they are projected onto. On the other hand, in the right hand pane, well, the shadows are projected by the computer. So these are the real shadows, and this is actually the point. So shadows like the ones on the left are simply not possible if the light comes from the left. They would have to be shadows like the ones that you see on the right. And still the visual system has no problem in accepting the shadows on the left as shadows and using them to reconstruct the scene characteristics, that is the relative position of the objects on the scene. Let me move on to another topic here, which is other cases of things that you can do to shadows. So you can hide shadows. It's quite tricky, but although these look impossible, but these are possible shadows because I took a picture of them, which look impossible. And here is also a case in which you have what looks as if it is an impossible shadow, the shadow of my hand going behind the shadow of this is flower on the floor. And we discover a number of other illusions. This is an illusion of a double shadow. It is as if the pen has two shadows, one that passes under the exercise book and another one which ends into the two cups. Shadow capture. The shadow up here in this Pontormo painting looks as if it has been captured by this element here, this person here, but actually it is the shadow of a statue over there. So there are proximity Gestalt rules for capturing which apply to shadows. This is another example of shadow capture. So these all appear to be shadows of this strange sculpture over here, and of course only one can be, and it is actually this one because of the shape it has over there, but they are plausible. Both this one and this one are plausible enough to be considered as shadows of this trunk over here. And the shadow capture has an impact. You can measure, it's not just it looks as if the shadow has been captured. It has an impact on the 3D structure. So here shadows, as we see in a moment, have been captured by some object. That is, this shadow does not belong to this object, but it belongs to this object. But because of the continuity here, it looks as if there is no step at this point. So if I move to the next picture, you can see that the shadow actually are climbing a step every time. So there is a step here. But in the previous image, the shadow of that object has been captured by this object. So shadow capture has an influence on the perception of 3D. This is the type of work that we do. Basically, we did in the book, looking at hundreds of different cases in which the visual system is trying to make do with what it has in order to reconstruct a scene, and is fooled by shadows in a systematic way. What we're looking for is systematic ways in which the visual system is fooled, so that we can say, okay, here there is a rule, kind of a grammatical rule, like the rule for forming passives out of active sentences. And that's it. So I thank you for your attention, and I'm very happy to take questions if you have questions at this stage.
And thank you very much. And of course, if someone connected online would like to place a question to Roberto, please use the chat. Yeah, it's okay. Thank you very much. Have a seat. Your usual. Thanks for your talk and the elaboration on shadows. So what struck my mind was that you kind of look at shadows as geometrical figures. So so they are kind of projections of something. But what about the notion that shadows are made of light, and light is not a ray, it's actually a wave. So there are many quantum phenomena that are also present in shadows. For example, that shadows can touch each other while the objects are not touching each other, which is an effect of diffraction. And I can, for example, also refer to one famous example of Karen Barrage, where she describes the shadow of polarized light, which is actually a diffraction pattern. I hope I didn't lose the connection.
Okay. No, I'm here. So thank you very much. Thank you very much. It's can you hear me? So the question was about different shadow phenomena which are related to more complex physical interaction than just the purely geometrical projection. Yes, of course, but this is a different topic. It's a topic for physics, and here we're just concerned with the geometric part for a number of reasons. One is because of historical record, and painters in the Renaissance are the painters which are mostly focusing on, because they were making discoveries about light and projections by using shadows. There is a small amount of literature, Da Costa Kaufman and other people, who are writing about the discovery of perspective out of the study of shadows. And they didn't have any good theory of shadows. So Leonardo, for instance, had a theory of shadows, which was completely absurd. It's like as if objects are projecting shadow rays out of them, and these shadow rays are creating shadows. So it's physically impossible, possibly inconsistent. So the physical aspects of shadows that might be of interest here are relatively marginal. They're related to some phenomena at, so for instance, on the moon, you can have some interference bands during an eclipse, but they're hardly observable. And most of them have not been used by painters. So as our topic is using painters' understanding of shadows in order to get some understanding of the way the brain processes shadows, this puts huge constraints on what we are looking at. And not all the physical aspects of lights are of interest here.
Thank you very much, Roberto. We will from here in our say, faraway monastery. We lost just a few moments of your last sentence, but I think that Klaus gets the answer he needed. So if there are any other questions, we will. Personally, what struck me is that a tool like an interpretation tool like a Gestalt is still so relevant today. This is what personally what my reflection is. So it's something that was firstly, let's say, a framework that come from near a century ago is still effective in our also in your research. You mentioned the Gestalt principle a couple of times, and so this is just I think I want to share. So, are there any other questions here now? No. So, I think that we are at the end of our third day of talk, and I really, really thank all the speakers for this really deep and really interesting morning. So I hope that there will be future occasion also to develop these topics. We have just started to develop in this point. So thank you all of you for being here. Thank you all the people here in Monte Compost, and also to the people who attended online. And thank you very much, everybody. And if you are interested in following tomorrow's talk, please connect at the same clock. And we'll have tomorrow morning. We have Maurice Benayoun, Marco Mancuso, and the presentation of two works from one from the Hungarian University of Finance and the other one from Abbas. So thank you very much, everybody, and goodbye. Thank you.
Thank you.
Goodbye.
Bye.